The sum of a sequence of unique positive integers in arithmetic progression was calculated as 5522. But it was realized that one term had been included 2 times. The sum was recalculated as 5020, but this time the same term was left out by mistake. If it is known that there were at least 15 integers in the sequence, which of these could be the total number of integers in the sequence? And we are given 5 options, a very typical multiple choice type of question that's common in GRE, SAT, CAT, and other standardized tests. So this is a very interesting problem, and what I will show here is a step-by-step solution which will hopefully make it easy to understand how to go about solving this and similar problems. So we begin by letting the sum of the AP sequence be S, and then assume that n is the number of terms or number of integers in the sequence, which is what we have been asked to find out. Now, from what is given here, if we assume that the term that was added twice first and then left out is AX, and in general A1, A2, A3, AN is kind of the numbers in the sequence. So AX was that term, and we don't know what X is. We don't know which term was left out in the sequence. So that's why we have that unknown X here. So when the term was included twice, then the sum must have been, the sum of the sequence plus that additional term that was included twice, right? So had it been including just once, it would have been the normal sum S, but now it's included twice, and that's why S plus AX is 5522. And similarly, the second time the sum was calculated, AX was left out, so that will be S minus AX, and that's given as 5020. So this is a simple set of equations, and it's very trivial to calculate what S is. So we add those two up, we get 2S equal to 10542, and S is 5271. And AX will be 251. So from this point, all we know is we have the sum of an AP series. So it's a certain number of integers, unique positive integers in arithmetic progression. So we know that sum S, and we know one of those terms in the AP series, but we don't really exactly know which term it was, right? And this seems like a hard problem from here on to determine what could be the total number of integers in the sequence, because we can start playing all sorts of guessing games, and maybe some of you will be able to figure out just from here by assuming different x's for the missing term, like what position in the sequence that could be, and figuring out different possibilities. But that kind of approach is really a trial and error kind of approach, and could cost you significant amount of time, and it's not really a good mathematical way to arrive at the answer quickly. So let me show you the correct mathematical way, and hopefully so my intention behind doing this is just to teach and propagate some good problem solving techniques, and take out the guesswork as much as possible. Though in some of these multiple choice questions, I do admit that guesswork can sometimes lead you to the right answer, but many times it can also lead you to the wrong answer. So let's now think about what is the sum of an AP series. Well, if we have n number of terms in an AP series, then the sum, and the terms are A1, A2, A3, so on up till AN, then the sum of the AP series can be represented as n multiplied by A1, which is the first term, and AN, which is the last term, or the nth term. In this case, the sequence is n terms, right? And then we have basically a 2 in the denominator, so it's the whole thing divided by 2. And what this essentially tells us that the sum of an AP series is the product of the number of terms and the sum of the first term and the last term divided by 2. And this sum we know is 5271. So now we know that the product of the number of terms n multiplied by the sum of the first term and the last term will be 5271 multiplied by 2. And if we break up this, so what we are trying to do is break up these into prime factors, right? And the reason for doing this is we know that both n has to be an integer, and since the sequence itself was a sequence of positive integers, we know that both n and a1 plus an has to be an integer, has to be integer values. So if we know the product of two integers, if it's given, then it's possible probably to determine to some degree at least a set of values that those two integers are likely to take in order to satisfy the product. So 5271 was a big number in this case, and we could see readily is divisible by 3 and further divide that result by 7, and that's how I break down into 251 into 7 into 3 multiplied by 2. And 251, I didn't bother to break it down further. And one of the things that's unique about 251 is it's a prime number, but breaking down up to this level, so even if it wasn't prime, I think breaking down up to this level is fine for this step. So what's the next step? Well, one thing we know is since we found the term that one of the terms of the AP series was 251, then the sum of the first term and the last term must be greater than 251. Why? Because in a limiting case, suppose AX, which we determined as 251, which was kind of the term which was included twice the first time and left out the second time. So in the limiting case, if that term is the last term, right, then of course a1 plus an is going to be greater than that because it was a sequence of positive integers, so a1 has to be greater than 0. And since one of the limiting values that ax can take is 251, so a1 plus an has to be greater than 251. But this is a limiting case, right? So usually, or in all other scenarios rather, I mean, ax will be somewhere between a1 and an. And we know that an and a1, they are kind of on the two sides, right? Because it's a AP sequence of positive integers. So a1 is the first term. Of course, in an AP series with a positive common difference, the terms keep on increasing, and these are integer terms, right? So that's what we expect, that a1 plus an should be greater than 251. So that's kind of a reasonable assumption, I guess, to make. So if that's the case, now we can start assigning values to a1 plus an, because we know a1 plus an has to be an integer. So a1 plus an is greater than 251. So the minimum possible value from that breakdown that we had earlier, that a1 plus n can take is 251 multiplied by 2, in which case n is 21. But this is not just the only case. There are some other cases too, or other values too, where a1 plus an satisfies their sum being greater than 251, and that would be a1 plus n equal to 251 multiplied by 3. So for n we have 7 and 2. 7 multiplied by 2 makes 14, so n will be 14 in this case. And this other possibilities like a1 plus n equal to 251 multiplied by 7, in which case n will be 3 multiplied by 2, 6. And then this possibility of a1 plus n equal to 251 multiplied by 7 multiplied by 3, where n takes the value of 2. So we are basically considering the factors that are greater than 251 from that product that we expressed, and we are basically evaluating, or listing all the possible scenarios of what values a1 plus n can take, and what's the corresponding value of n in those cases. Now it is given that this sequence should have at least 15 integers, right? So we can rule out all the values of n that are less than 15, which makes the only admissible value of n in this case to be 21. So the correct answer, or the correct option, would be the option B, which is 21.